Hello. So, this is a course on basic calculus. It is indeed the first part of the basic calculus course. So, I will be here to help you learn this topic, and this is lecture 1. We will be talking about the real line on which we have the functions, and we will be doing something with the functions in this course, which are defined on the real numbers to real numbers. So, now this real line will be the topic of the first lecture. We will be talking about many things about real numbers, but first let us fix some notation, so that it will be helpful to read the written text. So, the first is the empty set, which we write just like it looks like a Greek alphabet, Greek letter phi, but it is not exactly phi. We will call it the empty set, and then the set of natural numbers, which will be writing in the blackboard font n, which consists of numbers 1, 2, 3 and so on. Then we have the set of integers, which is z, which includes the set of all natural numbers, and along with that we have some more numbers, which are the minus of all those natural numbers and 0. So, we will writing like this, that is 0, 1, 2, 3 and so on the other side minus 1, minus 2 and so on. In fact, this other side business means they are ordered, but we will come to it later. And the set q, the set of rational numbers will be denoted by this q. A rational number looks like p by q, where p is an integer and q is a natural number. So, that 0 is avoided and negative numbers are avoided in the denominator, but often we write, for example, minus 2 by minus 3, where we cancel this minus sign and say it is 2 by 3. So, there is no loss in telling that all the rational numbers are in this form, which is p by q, where p is an integer, q is a natural number. Then we have the set R, which is the set of real numbers, our main concern. We will be defining it slowly. We will wait for some time what it is exactly. Then this R plus will denote the set of all positive real numbers. Among the real numbers, there are some which are positive, there are some which are negative, and there is also 0. So, the set of all positive real numbers is written as R plus. Similarly, R minus is the set of all negative real numbers. And now you can see it is in the increasing order, in the sense that the empty set is a subset of every set. So, empty set is a subset of n, and n is a subset of z. Set of natural numbers is a subset of set of integers, which is a subset of the set of rational numbers, which is a subset of R, the set of real numbers. But it is not only the subset, the sign here, which this one for example, it says it is a subset and it is not equal to that, the next one. So, that means it is a proper subset. So, all that we see here is the empty set is a proper subset of n, which is a proper subset of z, which is a proper subset of q, and that is a proper subset of R. And to the decimal representations, we know that this q, or the set of rational numbers, consists of all terminating or recurring decimals. So, that means, for example, you take 1 by 4, which is 0.25, it terminates there. After that, the digit 0 is repeated, which we do not usually write. But if you take 1 by 3, which is 0.333, the digit 3 is repeated infinitely often. So, it is called a recurring decimal, where 1 or some finite number of digits get repeated. That is the set of rational numbers. Each rational number can be written as a terminating decimal or as a recurring decimal. And the set of real numbers, if you take, which includes also these rationals, but it is a proper superset of rationals. So, there are some numbers which are not rational, they are irrational numbers. So, the set of irrational numbers we will write as R minus q, over using that minus symbol, which will be easily readable, that is why you take this minus symbol. R minus q will have again the decimal representations, which are non-recurring, non-terminating. So, these are the irrational numbers. For example, if you take a root 2, you take 1.414 and so on, it will never repeat, no digit will be repeated there. And you take another, for example, 3.1011, 0, 111, 0, 1, 1, 1, 1 and so on. So, here there is a pattern, we have just written the pattern here to show that something can be done, but it is not repeating. So, it is an irrational number. But these are exactly the decimal representation of real numbers. There is another alternative way of defining the real numbers. So, what do we do? In fact, what do we do with the real numbers? That question gives to some operations on the real numbers. So, we will define R in a different way, which will of course come to this. So, we assume that there are two operations defined on the set of real numbers. One is written as plus, which is addition, and the other is product or multiplication, which we write sometimes with this times symbol cross or with just a dot. And here we assume that multiplication has more precedence than addition, which means it will just curtail some brackets while writing. So, when you write A into B plus C into D, this will mean A into B first and then C into D next, and both of them are added. We will not interpret otherwise. So, that is the meaning of this multiplication has more precedence than the addition. So, we will just write A into B plus C into D and we will mean this, that is what it means. Also, this A into B will be written as A dot B, sometimes dot is also omitted and we just write A B. And these operations satisfy certain properties, that is what gives structure for this set of real numbers. So, the first is the commutativity property, which says that if you take A plus B or B plus A, no matter they are the same. Similarly, A into B and B into A are same. And there is further nicer thing for us, we can curtail many more brackets due to this associativity property. We say that A plus B plus C, so which means B plus C first obtained, then A is added to it. Is the same thing as A plus B plus C. On the right hand side we see that first we obtain A plus B, then add C to it, they are same. Similarly, when you multiply, you take B C, multiply with A and then take A B, multiply with C on the right, they are same. Of course, commutativity, so left and right will go away. We assume that there are two special numbers in the set of real numbers, which are 0 and 1. So, what do they do? If you take any real number A and add 0 to it, you will get back A. So, sometimes we say it is the 0 is the identity of addition. Similarly, 1 will be the identity of multiplication. We say any real number A times 1 is equal to A itself. Next operation is that corresponding to every A, we will have another number called minus A, which we are just writing as minus A. And what will happen to that? If you add them together, you will get the 0, the identity element of plus. And similarly, for multiplication, if you take A times 1 by A, you will get 1. But here we have a condition that A should not be 0, because we want to avoid that 1 by 0. So, A into 1 by A equal to 1 whenever A is not equal to 0. That is corresponding to any non-zero number A, we will have another such number, say 1 by A, which we write as 1 by A. When you multiply, you will get back 1. In fact, from all these properties, we will be able to find that corresponding to this A, this minus A is unique, corresponding to this A, which is non-zero, this 1 by A is also unique. Then we will assume that uniqueness here. And then how do they interplay? That is the distributivity property, that multiplication distributes over addition. So, A into B plus C will be equal to A into B, A into C, and both of them are added together. So, these are now 11 properties which happens for the operation of addition and multiplication. And over and above that, we have something else, a relation defined on the real numbers. It is a binary relation. It talks about two elements and what relation they have in between. So, suppose A and B are any real numbers and we have this relation we will write as less than, then this property holds, which is either A is less than B or B is less than A or A is equal to B. This is called the law of trichotomy, which holds for this order relation less than. Then we have the associativity, or sometimes called transitivity, which says that if A is less than B and B is less than C, this will say that A is less than C. This is called transitive. It is going, leaving that B inside. A is less than B, B less than C, therefore A is less than C. And we have another property how this less than behaves with respect to addition. It is really preserving. That is, if A is less than B, then A plus C will be less than B plus C for whatever A, B, C numbers are. And with respect to multiplication, we have restriction there, that if C is positive, 0 is less than C, A is less than B, then you get AC is less than BC. What happens when 0 is negative? We will come to it. It will follow from these properties later. And there is a notation here, for A less than B or A is equal to B, we will put an abbreviation, we will write A less than or equal to B. That is how we abbreviate these two things. And there is another abbreviation, we write A is greater than B for B is less than A. This is another symbol which is really coming from less than. Similarly, we will say A is greater than or equal to B whenever B is less than or equal to A. They will mean the same thing. That is the next property, which is the most important one and which helps really a lot to prove many theorems, which is called the completeness property of the set of real numbers. We will come to that slowly, but first let us see how these order relations are behaving. From the above properties, it will follow that if A is less than B, then A minus C is less than B minus C. So, what is the meaning of A minus C? It is again an abbreviation for A plus, this one really an abbreviation for A plus minus C. Similarly, on the right side, it is B plus minus C. So, this property says that if A is less than B, then you can take away something, say C from both the sides, and still the less than property is maintained. Similarly, if you take, this is what I was talking earlier, that if A is less than B and C is less than 0, that is C is negative, then the inequality is altered. It is no more AC is less than BC, but it is AC is bigger than BC, it is greater than BC. And if C is positive, remember that AC will be less than BC. If it is negative, then it will change the inequality. Now, if A is less than B, then minus of B will be less than minus of A. This is how you can now think how the other property is related. The sixth one, due to the earlier that C is positive, we will get AC less than BC, and negative you get this. This is now reflected here. If A is less than B, then minus B will be less than minus A. And if A is positive, then 1 by A is also positive. This also is another property which follows from the earlier order properties. If you take any two numbers, say A and B, such that A is in between 0 and B, so both A and B are positive, but A is less than B, then on the other side, when you take the reciprocal, that is 1 by, it will be reversed. You will say that 0 less than 1 by B is less than 1 by A. These are all the properties we know and we are familiar with, so we are just recalling, and it also fixes the notation. Now, we will be talking about the completeness property, for which we need a small definition, which will be useful and which will be helpful to write this completeness property in a compact way. So, suppose we start with a set of real numbers, and it is not a non-empty set, it is not an empty set, which means there are some real numbers in A. Then another number u, which will be from R, may be inside A, may be outside A, it does not matter. So, real number u is called an upper bound of this set A if each element of A is less than or equal to u. So, that means something like if your A is somewhere here, then this can be u. So, that u is greater than or equal to every element of A. That is how we say that u is an upper bound of A. and suppose we take one upper bound of A which is L, we will call this L, the upper bound, as a least upper bound if all upper bounds of A are greater than or equal to L. That is, it is the least of all the upper bounds of A. That is why we will call the least upper bound. Sometimes we just write LUB for this, LUB instead of least upper bound. And now the completeness property we can state, which says that every non-empty subset of R having an upper bound has a least upper bound in R. If you go to our earlier notation, so suppose you have some set A here and then you have some upper bound U, then you can always find something which is the least of all those upper bounds. That is what very obvious, but it is not satisfied everywhere. So, we will see for example, in Q it is not satisfied. Q does not satisfy the completeness property, because what is the reason? Suppose you take say set of all numbers which are less than root 2. We know that root 2 is not a rational number, it is irrational. Then its least upper bound will be root 2, which is irrational, which is not in the set in Q. So, R really satisfies, but Q does not. But N satisfies this property also. However, N is not equal to R, because there are some other properties which is not satisfied by N. Okay, so, most important of thing is inference from this completeness property is the so called Archimedean property, which says that if you have two positive numbers A and B greater than 0, then you will always find one natural number n such that n of A will be greater than or equal to B. So, this really strikes something. It is told in a funnier way because of Archimedes. So, suppose you have a very big bathtub and you have a very small spoon and you try to empty the bathtub with the spoon, then it says that after some time you will be able to do it. The bathtub will be empty by the spoon. So, it may take more time because this n can be large, there is no problem, but there exists one n such that n of A will be greater than or equal to B. This is called the Archimedean property, and use of this property is very much, but we may not really use it very explicitly, but there are some theorems where exactly this Archimedean property and this completeness property with its full strength will be used. So, now let us look at one property which follows from this Archimedean property. We are not going to prove it, of course, which is called the denseness of rationals. That is, suppose you are choosing any two real numbers x and y, where x is less than y, then it says that there is always a rational number between these two numbers x and y. So, here we are writing as A, that if x and y are real numbers, then there exists a rational number A such that x is less than A less than y. Similarly, the irrational numbers are also dense in R. That means, given any two real numbers x and y, where x is less than y, you will always find one irrational number B such that x is less than B, which is less than also y in between those two numbers. So, that is what we write, both q and R minus q are dense in R. These properties help us to visualize real numbers as the real line. The set of real numbers can be thought of as a real line. So, if somewhere we have to point out, say we have marked 0 somewhere and 1 is another, say unit length, this is our length. So, 0 to 1, then 2 will be here, they are the natural numbers 3, 4, and here on the left side we mark the negatives of that. So, we have the integers inside R, then we have rational numbers inside, you take any fraction, say 1 by 3. So, it is here, and that is marked on the real line itself, and there are also irrational numbers like root 2, which is between 1 and 2, also pi, irrational numbers, you will meet also E and so many others. So, we can think of the set of real numbers as the real line having this ordered property, which are on the left they are less, on the right they are bigger, like 1 is bigger than 0 and minus 1 is smaller than 0 and so on. This is how we can visualize the real line. On this real line, we are going to fix some more terminology. So, today we will be simply devoting most of our time to terminology, and these are called the intervals, very nice subsets of real numbers which look like real numbers, but their portion are like a line segment on the real line. So, suppose we start with some two real numbers a and b, where a is less than b. This notation which says closed bracket, closed left bracket, and then the right bracket. So, square brackets a and b, a b, this is how we write. This will denote the set of all numbers between a and b and including those two also. So, suppose a and b we write here, b and this is a. So, when we write like this, it means this consists of all numbers inside this along with a and b. The numbers outside in the real line, they are not inside that interval, they are in R of course. So, this is the closed interval, we will say closed interval a b consists of all these numbers. Then we have similarly left open. So, look at this parenthesis now, not the bracket, it is a parenthesis. So, open a closed b, we can read that way. It is a semi open interval a b which consists of all numbers in that closed interval except a. So, a is omitted, that is why this open bracket. Similarly, we have the other interval, on the left side it is closed, on the right side it is open. So, that means a is included, but b is not. So, it consists of all numbers, real numbers between a and b including a, but not b. Similarly, both can be open, so that both are excluded. This is called an open interval. Now, we introduce the symbol, this infinity symbol. This is not a real number, it is just a notation writing some set in this form, open minus infinity, b closed. It has to be open because minus infinity is not in R. So, this symbol is also called an interval. It means it is the set of all numbers which are less than or equal to b here, nothing out to the right, everything here is included. So, minus infinity, had it been there a real number, it is omitted, that is why this symbol, but in fact it is not a real number. So, it is just a notation that it is the set of all real numbers less than or equal to b. Similarly, we have the minus infinity b, where b is also open. So, it will include all the real numbers which are less than b. And then we have a closed infinity. So, again infinity on the right side we think, minus infinity on the left side. So, this a infinity will be the set of all real numbers which are greater than or equal to a. A is included, but nothing else, and everything to the right of it. Then we have open a, open infinity. So, that will include all the numbers which are less than or equal to, which are this is wrong here, which have all the numbers which are greater than a. So, this should be greater than a. It looks something like this. If a is a real number, then all the numbers here are inside this interval. A itself is not. So, we write like this. So, this is the set of all open, the set of all real numbers which are greater than a. And similarly, we can have minus infinity to infinity. So, that means all the real numbers, there is no a specified here. So, this is another notation for R itself. It is considered to be both open and closed infinite interval. Then we have the positive real numbers, which we can now write in this way, because this 0 to infinity both open means all the real numbers bigger than 0, that is exactly R plus or positive numbers. Similarly, R minus will be all the real numbers less than 0 which are negative real numbers. So, all these sets are called intervals. Whenever we write one of these, that is called an interval. So, when we let us say that let I be an interval, then it means I can be any of this.